Okay, so as I said, some of this will be new to you today because we're going to talk about springs, but some of it won't be because you did the conservation of energy last year. So you know that the law of conservation of energy means that the energy you start with in a system is the energy that you end with. I chose 3 different ways to say that, including the one I just said, so 4 different ways. I don't want you to copy down all of those points up there. I want you to read the one that sticks in your head and write that one down. Okay, because it's the same thing repeated 3 times. It's just a matter of which one do you understand. So that way, when I ask you what the conservation of energy is, you go with that. Right? So the first one's like your textbook definition. The second one's a short to the point definition. And the last one there, it's just a rewording of the first one. Right? So at the end of the day, we look at closed, isolated systems. So the mass is constant. The energy is constant throughout the situation. And it just gets transferred from what you have at the start to what you have at the end. Right? And whatever that transfer is, that's what you're looking at. Any conservation law is the same, right? Conservation of mass, with the mass you start with is the mass you finish with, right? Conservation of momentum, which we're going to do later in the week. Same thing though, the momentum you start with is equal to the momentum you end with. The only time that conservation of mass doesn't really happen is when you have a nuclear reaction and some of the mass is lost because it's converted to energy. Now, there's no technology yet that takes energy and converts it to mass. That would be cool if there was. It'd be like in Star Trek when they beam people up. Take a light energy and convert it back into people. Are we good with the law of conservation of energy? So when we look at every problem from now, like for this week, I guess, and in our fields unit, we come back to energy too, right? We're always looking at the start and the end. There will be questions I'm going to throw at you which will have a middle part to it, but we don't care about the middle part because we only worry about the start and the end. They're all closed systems, so we only worry about, like, if you have a cart going down a ramp, right? We worry about the top of the ramp and we worry about the bottom of the ramp. We don't care about the in-between part, right? Or if you go back to that pogo stick question we just did, right? We care about how high he starts with or falls from and how much the spring compresses at the bottom. We don't care that it gets converted into kinetic energy in between because we only worry about the start and the end. That's what makes energy really special in terms of looking at the world, is because it gets rid of the complex process of what happens when things actually interact, and you're only looking at the start and the end. And you're also only looking at the scalar part of it. It's all scalar, right? So there's no directions involved. So it makes it easier to look at scenarios too. There is this slide here, which we didn't talk about last week, but it may have popped up in your homework, something called the work energy theorem. And it's just a different way of explaining the conservation of energy, but from a work perspective. So when you have work in a problem, so if work becomes involved, your work changes the kinetic energy of your system. So you can have positive work or negative work. We talked about this, depending on which way it is in reference to the displacement. And in the work energy theorem, it's about doing work and objects speeding up and slowing down. Why this is important is because when we talk about momentum, there's also a theorem related to momentum that's along the same lines as this one. Most of the time, again, work is either somebody pushing an object causing it to speed up, or friction acting on an object and taking energy away from the system and converting it to heat. Any questions with this theorem? As I said, it's just a different way of explaining the conservation of energy. I don't think you have to write this down. I only put this slide in here because sometimes you see the word mechanical energy, and you may have talked about it in grade 11 as well. Mechanical energy is a physics term that relates kinetic energy and the potential energy of a system together. So sometimes if you are looking this up online later, you'll see graphs like this one where it has KE and PE. So it doesn't say which type of potential energy is, right? We know there's 5 of them. And we don't know what type of kinetic energy that is. We know there's 4 of them. But it's the sum of the two together, and the system stays constant. So if you go through and do all the math in your head, you'll see that they all add, each stage here adds to 50,000 joules, right? Because your energy of your system stays constant. It converts from one to the other as it goes. And in physics, we call the combination of those two together, when you add them, that's your mechanical energy. So it wasn't on our list of the 9 energies before, because it's not an energy by itself. Sometimes you'll see online that it does mention it by itself. So if you are looking up energy transformation equations are a good one. You'll see that anytime there's a car involved in it or a machine, it says mechanical energy. But that's wrong. That's not a real type of energy. So just be careful with that. So that's why I threw that up there, just in case it pops up in your notes. Or sorry, in your research later, if that's something you do. With the hammer here, right, we have a person picking up the hammer. So he gives it kinetic energy to lift it up, and at the very top of its swing, it's potential energy, gravitational potential. And then as he brings the hammer down, that would be your mechanical energy, because it's a combination of potential into kinetic. And then he hits the hammer, and that does something too. Any questions with those definitions? So I have this demonstration here. It should, I didn't test the link, so I'm hoping it works, but there's a website, I don't know if you've ever gone to it, probably not. It's by the University of Colorado, and it has all these little fun graphs on it. So we'll go to here, or activities. So here you can see we have a skateboarder. I'm just going to make a half pipe real quick. And this is just kind of a visual way of just making sure we understand what I was just talking about. Where's my pie chart? You guys like pie charts or bar graphs? The bar graph. So we know there is no friction here. So I put the skateboarder on the ramp here, right? So wherever I lift the skateboarder up, they're going to have potential. They're going to have your total energy, and again, you have your kinetic and potential energy, and that add those two together, you get your total energy, right? So if I let the skateboarder go and they go back and forth here, you'll see that the kinetic energy. Well, that didn't work very well. They're not supposed to fall off. There we go. There we go. So you'll see that the green bar and the blue bar always add together to be the yellow bar, and the yellow bar never moves. Why does the potential energy never go away? See, kinetic energy goes away, but why doesn't the potential energy never go away? Brian?
Because there's always potential energy due to gravity.
I can make it go away though, if I wanted to. Why doesn't it go away though? Because you're right, gravity's always there, so it could always be there. Jake?
It's probably relative to the ground and he's above the ground.
Yeah, good. So remember that gravitational potential energy is about a reference point, right? A reference level. So in this program, the reference level is the ground. So because I made my ramp floating in the air, the skateboarder will always have potential energy in reference to the ground down here. Right? If I take my skateboarder here and put this on the ground, or not the skateboarder, I'll just throw it over there. Right? If I put this dot on the ground down here and now put my skateboarder in, right, you'll see that the potential energy disappears because they go down to the reference level. Right? And the blue and the green bar will always add together to be the yellow bar. Right? Because that's the total energy of the system. So that's the conservation of energy as we were talking about it. The next part here though, I'm going to add in friction in a second. You can see as well, before I get to the friction part, if I just make the skateboarder larger, right? The mechanical energy gets bigger because mass is a factor. Right? But you'll see that the speed doesn't change. So if I put the speed, right, it almost goes up to that 12 o'clock position. And if I make them lighter, the speed doesn't change where they go up and down. The energy changes because mass is part of those equations. But the actual, when we do the math in a second, you'll see that the mass doesn't really affect the speed wherever you are on there. I make their mass the same. The last part is with friction. So I'm going to stop the skateboard here in a second. With friction, there's a couple of energies that I personally call waste energies. So thermal energy is one of them. Sound energy is one of them. Light energy is one of them. And the reason why I call them waste energy is that when they are present in real world situations, they're always present. They're not recoverable. So you can't take back in the thermal energy that's lost because of friction and reuse that later on in the problem. Right? The heat energy disappears in the air and you never get it back. So when you look at this, so what I mean by this, if I add friction up here, what you're going to see is that the total energy of the system again never changes. The energy at the start is equal to the energy at the end. But what's different is that the skateboarder is going to slow down, which you would have predicted because friction slows things down. So you'll see the thermal energy graph slowly increase, and then that decreases the energy from the potential and the kinetic because you can't get that thermal energy back. So even though the system's still following conservation of energy, right? So the heat's still there, or now it's not there, it's been lost. And the potential and the kinetic and the thermal all add together to be the total energy. So the conservation of energy still holds true even though the thing slows down. A lot of time I read on projects that you guys are doing that the conservation of energy doesn't hold true in the real world because things slow down. That's not true. They do slow down because your heat, once it's converted to heat, right, that's a measurable amount of energy converted to heat, but you don't get that back in terms of the motion, right? Like you sometimes see that in new car technology because they have, I know there are some cars that have they're electric cars, but they can recover your kinetic energy of your car. If you step on the brakes, it uses the kinetic energy of the car to recharge the batteries. So you can recover some of the energy that way. That's what a hybrid, what are they called? Not the plug-in hybrid, but the ones that are gas-powered hybrids, right? That's how they kind of work. They use the kinetic energy of your car to charge the batteries, which power the electrical components in your car, but you don't have to plug your car in. So that's kind of what's going on there. Any questions with anything that we talked about in regards to this graph here? All right, so there's lots of, the normal force really increases down here in the bottom. So that's why there's a big spike in thermal energy. If I made that transition a little bit less extreme, which I could do by doing this, right, you'll see that the thermal energy doesn't increase as much because they're not, the centripetal acceleration down there at the bottom is not as extreme. So this would be a slow, gradual come to a stop. So that's your conservation of energy up there. Any questions with before we get into the new topic, which is simple harmonic motion, which is also the conservation of energy, but it deals with springs. I'm just making it bigger again. So I'll give you guys a second to copy down those words, and then I'll talk about what it means. What we're going to do, just to give you guys a framework here, because I talked more at the start of class, we'll have our break after we're done our notes and before we start our examples. So I haven't forgotten, we'll just have to wait a bit longer to get to the map, which is fine. So when you're reading this, there's a couple of things I want you to unpack out of that first sentence. There's a lot going on there. Simple harmonic motion, I'm just going to tell you right now, it doesn't really exist because friction plays a role. So in our ideal world where friction doesn't play a role, you would have simple harmonic motion. We have things that are pretty close, but we all know that friction always is present, which takes energy out of our system. And we're going to talk about that on the next slide. Here, for simple harmonic motion, it's a back and forth motion. So I'm sure you can think of many things, either that you've done personally or have seen, that involve something going back and forth, right? So it's a back and forth motion. So you can think of something in your head. For simple harmonic motion, it has to have that. Unimpeded going back and forth. The second thing is that it has to have a force that wants to bring it back to the rest point. So whatever you thought of about going back and forth, you have to think, okay, is there a force there that's bringing me back to the rest point? So a rest point could be in the swing, like if you're on a swing with a friend and the swing is just hanging there before you get on, that's its rest point. Right? Gravity is always trying to pull it back to the bottom, but your momentum carries you, or inertia is carrying you up as you go through the bottom up to the other side. Okay? If you're in physics class and doing the beat test, that's not an example of simple harmonic motion. Because even though you're going back and forth across the gym in a periodic motion, right, there's no force pulling you back to the center of the gym once you pass it. Right? You just run to the other wall. And then you go back to the other wall. There's no force. And if you stop running, you don't gravitate back towards the center line of the gym. Right? Because that's kind of what would go on here. The second thing is that the vibration has to have the same amplitude and frequency. So whatever is happening here, the amplitude has to stay the same, and the frequency has to stay the same. So if you pluck a guitar string, that vibrates at the same frequency until it runs out of energy, but the amplitude decreases as it goes because the energy is dissipating into the air because of friction. Right? You know eventually the note runs out. Right? You hit a note on the piano, it makes a loud noise at the start, but then it fades away. In simple harmonic motion, that note would never fade away. It would just be there. It would be really annoying for any type of music. So I put this picture up here. You have the pendulum, which is probably the easier one to see, because the pendulum's going back and forth, and that little green arrow there is supposed to be the speed. You can see it increases as it gets to the bottom and then decreases. But we know gravity is always pulling it back to the middle. This spring one is actually a better one in terms of which way the forces are going, because you can literally see it in the green arrow on the top. Right? So the rest point for this box here is where the two colors meet here in the middle. But in each case, it has a spring pushing it back towards the middle. It could only just have one spring too. It would work the same way. So the restoring force is a spring always pointing towards the middle here. And this purple arrow is the speed. You can see that changes. And the acceleration, as we know, changes because the force of a spring increases with the more it's stretched. So that's simple harmonic motion. Again, this animation will go on forever. Right? This will go on forever because there's no friction involved there. And that's what's great. What is reality is something called damped harmonic motion. So these are all motions that are, again, could be simple harmonic motion if friction did not exist. Now there's three types, and I'll explain what each of the three are when you write it down here. And I have slides for each of the three types, so you don't have to worry about writing things down when I talk. I want you to look at the animations up there, especially the one on the right when you have that sentence copied down, and tell me what the difference is between the three types of damped harmonic motion. Right? Talk to your elbow partner. What's the difference between the three? You have over damped, critical damped, and under damped motion. All right, come up with your own definitions here. You can look at the graph too on the other side, but the animation I find is much more helpful. All right, talk it out with your elbow partner. I'll give you 2 minutes to figure out your own definitions.
Get it up here, but it's not coming out of here.
So pretty much every time this guessing is that it reaches.
Like it's slowly, it goes on slowly. Like it reaches like slower.
Okay. Yeah.
Over there too.
And then it also goes past the equilibrium. Critical and over damped never go past the equilibrium, but critical damped reaches the equilibrium at a faster rate than under damped.
Does go, it goes past equilibrium, but it keeps getting smaller and that until it gets
The red and the green one is more practical, they occur, but like the purple one go really deep and then go really high again until it stops.
like critical and over that, like they go down at certain speed to
Okay, so which one did you find the easiest to define or describe? Green, red, or blue? Any takers? Which one is the easiest one to talk about here? Anybody find the blue one easier to describe? That one moves the longest. I got one. Anybody, how about the green one? Couple greens, any reds? And one red. What did you guys say for the blue one? Under damp motion, what is that? Well, how do you describe that motion? No takers, eh? Sloan, what did you guys say?
We said that it like quickly goes down and past the like equilibrium point, and then the displacement to the maximums decreases over time till it eventually stops.
Yep, good. So the blue one there, right, slowly comes to a stop. It vibrates on both sides of the equilibrium point as it kind of slows down. Any idea what, like an example of that would be in the real world? There are lots of examples. But you've never thought of it before, Brennan?
If you're swinging, but then stop pumping your legs.
Yeah, perfect. Yeah, you're swinging, stop pumping your legs, right? You slowly come to a stop. Any other ideas that would slowly come to a stop? That involve springs?
If you like bounce a basketball, it'll like bounce and then bounce and bounce until it slowly like stops bouncing.
So that's a good non-example of this.
Not really?
Because there's no equilibrium point in the basketball.
You're right.
Right?
Yeah.
It has to go around the equilibrium point. A basketball is at the ground. Right? So it doesn't go past an equilibrium point. So that's what I see a lot. That's not a good answer.
Yeah, bouncing on a trampoline.
Bouncing on a trampoline would be one for sure, right? Because your surface of the trampoline, right? That would be the surface of your trampoline. And if you just stop putting energy in there, you just bounce to a stop. That would be one. Brennan?
Bungee jumping.
Bungee jumping, yeah, good. Yeah, slowly come to a stop. Right, but you have to remember that you have to go across this equilibrium point or rest point. Right, if it doesn't have a rest point or equilibrium point, it's not simple harmonic motion. Did anybody have a good definition for the green one or a good explanation for what's happening in the green one? Nobody? I have to choose somebody again. Annabella, how about you? I haven't heard you yet today.
We just, I don't know, like we kind of just compared it to like the overdamped and just kind of said like it reaches the equilibrium point like quicker than the overdamped. I don't know.
Yeah, good. Yeah, so the critically damped, right, hits the equilibrium point faster, so it comes to a sudden stop. So it's still spring-based, but normally in a technology you could have a fluid in there that slows it down to a good stop, or something else that snaps it back to its position. Any idea what would be an example of something that's critically damped? So something that uses a spring or periodic motion, but when you fire the spring, it comes to like a quick stop. Yeah?
A mechanical pen?
Yeah, mechanical pen would be one, right? You click your pen, it comes to a stop right away. Right? The stopper on it. Shocks in your car, not that you think about that, or on a bike, were critically damped. They get compressed, but then they shoot back to their rest point right away. They don't. If you have ever seen a old car that has bad suspension, like if you're buying a used car, one thing you might do is like press down the trunk or the hood and let go and see if the car, when you press down, should go down, but when you let go, it should just go back up and stop. And if it has bad suspensions, it will bounce a little bit after you let go. You see that a lot with trailers too. Like if a trailer goes over a bump that somebody's towing behind their car, right, it bounces a little bit on the ground, right? That's not really critically damped. A lot of athletic equipment is critically damped, like a hockey stick, a golf club, anything that involves anything that you swing where it bends or flexes, right, is critically damp because you want it to snap back into its rest position right away, and you don't want it to go past its rest position, and that would just look weird. And you'll see that on the next couple slides too. What did you guys say about overdamped? What about overdamped? The red box, that's the one we haven't touched on yet. What's happening there? Eric, what's happening on the red box there?
I would say it's similar to like the green one, except that it's the equilibrium point slower.
Yeah, it gets the equilibrium point slower. Yeah. Any idea where you would see the over-damped motion? So it's returning to its equilibrium point, but it has something to slow it down so it doesn't snap shut. Some of you might have these at home. Brennan?
The slow closing cupboards.
Yeah, slow closing cupboards or drawers, right? They have a system in there that you slam it, but then the last little bit closes slowly so you don't pinch your fingers. So these are just the definitions, whether you want to write them down or not, that's up to you. All right, so underdamped is, we use a swing, and that was our example. It's also the blue box on here, right? So the black box is on simple harmonic motion, never stops. But the blue box, you can see, slows down over time and eventually comes to rest. That's deceptive because you think the blue box, the frequency changes because it doesn't vibrate as high, amplitude decreases, but it's actually the same frequency. Overdamped means that it slowly comes to a stop. Right, so I put a picture of the door thingy up here. Right, it works the same and pulls the door shut slowly so the doors don't slam shut. If you go across the hall to the geography or history classes, right, they don't have those on their doors, so you could slam those doors shut. Science, you can't slam doors shut. We have them on our doors because our doors should be shut at all times because it's a fire hazard to keep them open. So again, it goes back to its equilibrium point. So that's a big key here. So if you have a ball, right, that bounces off the ground, again, it's not bouncing balls don't have equilibrium points, so it wouldn't fall under this. Last one is the shocks, right? So we have, it's critically damp. So we have, I can show the video in a second too, right? But all of these, the springs bounce back to their equilibrium point as fast as possible, and they don't go past it. So they have something on there that controls what they look like. And as you copy that down, I can show the video up here of the good shock versus bad shock, and then you can actually see what it looks like. So the bad shock, when the tire goes through the pothole, you can actually see the tire bounce in the air. That's like super bad shocks. And then the good shock, right? This is a better picture of it. So you can see how the old shocks, when they hit bumps, right, the tires lose contact with the ground, which is not safe in a car because all your safety comes from having good grip. And then on the other one there, the good shocks are critically damped so the tire stays in contact with the ground really well. I put a picture of a golf club up here because golf clubs bend when you hit them. And if you have the wrong flex in your golf club, say with hockey sticks, then the club's not lined up properly when you hit it, and then it changes the flight of your ball. And there's a video here too, I'm not going to watch it right now, about how the suspension system on an F1 car works. They are super high tech. All right, so that takes us to the end of our notes. So just a final check-in, what are the numbers that go into these boxes here, these blanks? All right, Jackson, what goes in this one here? What do you think?
I'm not sure.
Well, how much did we start with up here? So in A,
0,
we started with 0 and?
1, 4.
Right, so if we're at B here, right, what's the total energy of our system based on A?
Oh, 0.4.
Yes, that would be 0.4 there, yes, because that all has to add to 2.4. What goes in this blank right here? And?
2.4.
2.4, right, because it's all kinetic energy at the bottom. And then what goes into D right here for the two blanks down here at the bottom? Sloan?
0 and 2.4.
0 and 2.4, right? Because it all adds to 2.4 as we go through there. If we take a look at the skier here, which situation is he going the fastest at 0.3? Sorry, not 0.3. I was looking at the bottom there. This point here, this black dot, so 0.1, 2, and 3. Okay, I'll give you a minute to talk with your elbow partner. You guys can decide if it's situation 1, 2, or 3. Which skier is going the fastest at that black dot?
Tricky answer, I'm pretty sure. Actually,
Talk it out, talk it out.
either it's 2 or it is equal, because I'm pretty sure they're all coming in like at rest, like they're starting to rest. Does that make sense? Because like you're at the bottom now, so you don't have any more gravitational potential energy. So the kinetic energy should be the same.
That's the
That makes sense. Or I could be wrong. I don't know.
So it will decrease.
Oh, because you have the same height. Like height is equal.
For the one is too long.
And it looks like they're stopping. So, assuming since friction is a dimension, we can assume that the gravitational potential energy would equal the kinetic energy at that.
When it travels, the velocity decreases.
I don't know why don't we just take it like 10 minutes?
All right, time's up. Any votes for skier 1? The skier 1 again, any votes for being the fastest? He has a steeper slope and then goes off a jump. Nobody for skier 1. Anybody for skier 2? It's a quick hill down to 0.2. All right, seems to be most of you. Anybody for skier 3? The gradual hill would be a green circle at Chicopee. Anybody for none of the above? They all get there at the same time. The answer is none of the above. They all get there at the same time. I know it wasn't an option. You can make it your own option though. So when you look at this up here, I know that all of you picked this one here. I'm guessing, I don't know, but I'm guessing you picked this one because it's steepest. And the skier does get to the black dot the fastest, because their distance is the shortest to get there, and their acceleration will probably be the fastest because it's on a steeper slope. We just finished forces, so that should make sense. What you're not seeing though, if you chose that, is that it is the same change in height for each of these questions up here. Even though the distance or route they take to get there is different, the change in height for each skier is the same. So using the conservation of energy, they all have the same gravitational potential energy at the top. So that means that they all have the same kinetic energy at the bottom. right, as it goes from one to the other. And since the mass of the skier doesn't change as they go down the hill because it's a closed system, that means the speed will be the same at the bottom. Just different ways to get there. So the time it takes to get there is different, the acceleration is different, and the distance is different, but the actual speed at the bottom will be the same. Got you on that one. I got two more. So this one here, where is a roller coaster going the fastest, and why can't hill 3 be higher than hill 1? Right, I'll give you 2 minutes to talk that one out. Or a minute. We'll give you a minute this time.
Because there's it can be higher than hill 3 can be higher than hill 1 because otherwise it will have energy to go over.
Say again?
Hill 3 can be higher than hill 1 because otherwise because it's you lose energy to friction. So in like an ideal situation, it would also be 35 meters tall. But because friction, then the energy loss in the system, so it must be lower than 35 meters tall. I haven't done this in so long. I haven't done pick up the skin of my nails in so long.
Same.
All right, let's take this up. Jaden, where is it going the fastest?
I said 2.
Why'd you say 2?
Because it's at like the bottom of the hill.
Pardon?
Because it's at the bottom of the hill.
Okay, so using our theme of the day, conservation of energy, why is it the fastest at the bottom?
I just said that was my logical answer. It's not my scientific.
Maddie?
Because the gravitational energy will be the lowest there, because the height's the smallest, so there will be more kinetic energy.
Yeah, perfect. All right, so you have the biggest change in energy, right, from gravitational to kinetic here, so it's going to be going the fastest down at the bottom of the first hill. Why can't 3 be taller than hill 1? Sophie?
Like you won't make it up the hill if it's higher.
Why not, though? Use our theme of the day of conservation of energy. Any ideas? Brennan?
There's going to be some energy loss because of friction. That will create heat and that will be lost in the air.
Yeah.
So you have some energy loss from the system. Assuming there was no friction, though, then hill 1 and 3 could be the same height.
Yeah, so hill 1 and 3 could be the same height without friction. Real world, there's friction. So 3 has to be lower than 1 because all roller coasters after the first hill are usually gravity powered only, right? So whatever potential energy you have here at the start is what you have for the whole ride. So if your next hill is taller than the first one, you literally don't have enough energy to get to the top of the hill. So it will get wherever it stops and then roll back and forth and get stuck. So that's why if you go on any roller coaster, the biggest hill is always at the front, and then the hills get lower as it goes throughout the roller coaster. And if it's a long one, it might have a spot where it has a machine to pull it back up to the top of another big hill to keep on going. Right, just depending on the size of it. The last question here, I think it's about a hockey puck, if I remember correctly. So a hockey puck slides along a level surface, eventually coming to rest. Is the energy of the hockey puck conserved? Why or why not? Last question. You have 2 minutes to talk to your elbow partner, and we'll go for a walk.
Well, that depends if you consider waste energy being conserved.
Yeah, because it kind of depends because if you see like the thermal energy as conserved instead of transferred or converted, then like yes, it would technically conserve thermal energy.
And then the opposite could be argued. If you say that a waste energy doesn't technically follow conservation of energy. I want to take a nap.
Me too, I'm so tired.
Oh, there's a lot to do.
All right, what's the answer here? Is the hockey puck's energy conserved? Yay or nay? Patty?
Yes. It does. It is conserved.
And how is it conserved if we're coming to a stop?
Well, the gravitational energy is the same throughout because it's just on it's zero basically.
Yep.
But it starts with kinetic energy, and is affected by friction.
Yep.
So,
Where does the kinetic energy go then?
well, by the end, there's no kinetic friction. There's just
No kinetic
stop.
energy. Sorry, I say kinetic friction. I meant kinetic
Oh,
energy.
sorry. Yes.
Yeah.
It's just. Well, it's just affected by friction. Then I don't know how to explain how that would affect the energy, but it's affected by friction.
Friction does what? What does it do? Start with a W.
Work.
Work. Yep, good. So when your hockey puck's going, right, your friction does work on it. So your system of the hockey puck stays constant, but again, it's an energy that's not recoverable, so as it converts to thermal energy, you get, X number of joules of thermal energy, and that takes away from the kinetic and it comes to a stop. Eventually, all your kinetic energy at the front is all thermal energy at the end. Okay? So the answer is yes. Okay, let's go for a walk. We'll do a quick lap around. Probably the rest of it. And we're going to look at problems together and solve them together. And then depending on how far we get, tomorrow, we'll just kind of keep on doing what we're doing. So this is our first time solving a conservation of energy problem together. So I'm going to walk you through the steps that go with each problem. So again, the questions are on the slideshow, so you don't need to copy them down. We're going to jump right into solving them, but just like our force problems, there's a lot of thinking that happens before we get our calculators out and do some math stuff. Okay? So we read the question here. Andre is standing on top of the edge of a 3.7 meter high cliff overlooking a lake. He throws a 2.5 rock directly upwards with a speed of 12 meters per second, and it eventually lands in the water below. What is the speed of the rock just before it hits the water? All right, so that's what we're looking at here. So we're going to do our calculations to figure out what the speed of the rock is just before it hits the water. So you see a few things in the wording. You'll see that everything, just like in projectile motion, it's just before it hits the water, because at the water, obviously, a lot of things happen and we don't care about any of them. So it's where we start, where we finish. We don't worry about that it goes up and hits a peak and then falls down. We're just, as I said, worried about the start and the finish. So first thing on our list is going to be our system diagram, as always. Right? So if you're not in the habit of doing that yet, you need to start soon. Because these are not vectors, we don't need a compass system. But we do need to have one other piece that we haven't done before. So we have a general picture that looks like that. We have a rock going up and down, hits the water below. Okay? We know that there is an initial speed going up, so we can label that. We don't have to label gravity because it's not a kinematic problem. But we do need to measure or indicate where we're going to measure our heights from. Right, our reference level, which is new from anything else we've done. So my rule of thumb that works for me is I always make the lowest point of the problem my reference level. So that way all my heights are always positive in my equations. You can do it differently and we'll get the same answer in the end. So what I mean by that is that my final height, so my HF, is going to be 0 here at the bottom. And I have a VF going down. And that tells me that I also have an HI, or initial height. So I's are initial, F's are final. The reference point's the big difference, right? That's not something we've done yet. And it only applies to energy problems, so just make sure you have that step. Part 2 is the energy transformation equation for the problem. So here's where we're going to list out the energies at the start and at the end. So based on our system diagram, what energies do we have at the start? Andre, what energies does a rock have at the start?
Potential energy.
Which specifically, there's 5 potential energies.
Like gravitational potential energy.
Yeah, good. Does it have anything else?
That's a initial velocity, so would that be considered kinetic energy or no?
Yeah.
Okay.
Moving, right? If it's moving, it has kinetic energy. And what does that get transformed into at the bottom of the problem? So at the end. Marianne?
Wouldn't it just be kinetic energy?
It's just kinetic energy at the bottom. Okay, so gravitational potential energy at the start because it's above our reference level, and kinetic because he's throwing the rock. We're not worried about that it actually goes higher and then falls, because that doesn't matter to us. We're only worried about the start and the end. So that's why it's just kinetic energy at the end. Does that make sense to everybody? So there are different ways I've taught how to solve these problems, and it depends on what you'd like to do. I'm going to show you a very weird way of doing it that some students like, and I'll show you different ways as we go, right? We all know the next stage is our table of values. So you have to organize that in something that makes sense. So what I'm going to do is I'm going to make a table of values under each equation up here that I have, right? Because I know my gravitational potential energy has the equation mg/h. So I know the mass of the rock, right? 2.5 kilograms, 9.8 meters per second squared, and 3.7 meters. All right, so I have that. I know my kinetic energy equation is half mv squared, so I gotta have an m, and this time I have a vi. It is the initial side. That's 12 meters per second. And again, this is 2.5. And then it flows into kinetic energy at the bottom, right? So I have, again, my M. I'm trying to write this out. And the F, so I don't know, in meters per second. I said this is a weird way of doing things because obviously I wrote mass up there 3 times and it's the same object, so I don't really need to do that. But I know some students like the visual aspect of it, that it just has the variables listed for each equation we're going to use. Again, it's up to you how you want to communicate your understanding. If you just want one table of values that just has everything listed in it, that's also fine. There's no wrong answer or wrong way to do it. All right, next step. So we have diagram, step 1. Energy transformation equation 2. Table of values 3. So if I was writing this down, maybe I'll write this down just so I remember. So we had step 1 was our system diagram. Step 2 was our energy transformation equation. Step 3 was a table of values. So the next part is the law or concept, which is what we've been doing this whole time. I don't know if I explicitly said that before, but it's helpful. So we're all doing the same law here. EI equals EF, right? We're using the law of conservation of energy because that's our theme today. All right, we also did Newton's laws of motion last week, right? Where we said the net force is equal to ma. So we did that step 4 all the time. In this case here, I'm letting you know I'm going to use the conservation of energy to answer my problem. Step 5 is to solve the problem. All right, so we want to make sure we solve properly, communicating all our steps. There's 2 ways you can do this next line. And I hesitate because I don't know which one I want to show you. I'm going to show you the extreme way and then the short way. So I'm going to show you 2 things. Again, it's you choose what you want. So watch this one here. This is how I do it in my head. And so I'm going to communicate it to you. Again, so I got a lot going on there in my head. So these are all the options that we could have in a problem. You could have 8 things, like we could actually have to use 8 different equations up here. What a question that would be. But I don't think I've ever seen a question that has them all. So in my head, this is how I think when I get to a conservation of energy problem. I go through and I ask myself all these questions. So I don't ever write this out, really, but I do it in my head. So I write it out for you so you can see what I'm thinking. So I go through each of these and ask myself yes and no questions. So I ask myself, is my object moving at the start of the problem? Which in this case it is. So I know I have initial kinetic energy. I ask myself next, is my object above or below my reference level? That I've stated, which in this case it is, right? Because it's above my reference level. So that's still there. Does my problem involve, is there a spring? And if there is a spring, is it stretched at the start? And I do not have a spring this time. So I can cross that one off. Do I have a person or a machine giving my object energy in this problem? And the answer is no. Right? So I can cross it off. Is my object moving at the end of the problem? And the answer is yes, because that's what I'm trying to find. Is my object above or below the reference level at the end of the problem? Yes or no? And it's at my reference level. So I don't have that anymore. Is there a spring that's compressed at the bottom of the problem or stretched? There's no springs involved here, that disappears. And was there friction mentioned in this problem that I should care about? Or a machine that took energy out of my system? And the answer is no, because there's no friction that I care about. Okay, so even though I start off with a line, you can see that 5 of the 8 things actually disappear. But in my head, that's what I'm doing whenever I tackle these problems. I just, I do it fast because I know what I'm looking for. You're new, so maybe it's valuable to you to go through this and check things off as you go. Obviously, it takes another minute or 2 when you solve the problem, but it's worth it in the end if you don't miss anything ever. Right? The other way you can do it is obviously you can look back at your energy transformation equation and convert that into the same thing. So I would have EGI plus EKI. Order doesn't matter when you're adding here. All right, so you have initial gravitational plus kinetic equals final kinetic energy. Right, either or. I just wanted to show you how I think. I won't do that second line again. I just do it once for this question. You can do it for every question though. And maybe you should until you get comfortable and you know you always have the right answer. So the next line, right, we put in the equations for the quantities that we were trying to find. How can we simplify this line to the next one?
Masses cancel out.
Yeah, our masses cancel out. If we don't have work or a spring, the masses always cancel out because there's a common factor up there. So I can cross off these guys. And a personal preference of mine is I don't like fractions. So what I also do is I multiply both sides by 2. That gets rid of all the fractions all the way across. Not something you have to do. The Mr. Arkell thing up here. Alright, so it simplifies down a little bit. I know some of you might go off and find the gravitational potential energy on your own, because obviously you have all the components of it, which is fine too, but the masses cancel out, so it saves you steps. Does that equation look familiar to you, by the way? Marianne?
It kind of looks like one of the kinematic equations.
Yeah, so this equation is one of the kinematic ones, right? One of our old friends. Back to haunt us. Right? The Vf squared equals Vi squared plus 2a delta d. Right, it's there. Just popped up. Alright, and then we can just throw in our numbers and get our final speed here. We have 2 times 9.8 meters per second squared times the height of 3.7 meters plus 12 meters per second squared. Yeah. Try it on your calculator, make sure you're getting the right answer, right? You don't square everything last, instead of squaring the 12 first. And a good therefore statement, let's do that. When I was hiking yesterday at Mount Nemo, my kids wanted to do this, to throw the rocks off the cliffs when you're... Mount Nemo, if you have not been there, is right on top of the escarpment, and you can stand there and see all the way down to downtown Toronto on a good day like yesterday. So they're up there really high. I explained to them that there might be people or animals down below that might not want to get hit with a rock.
Possibly.
Which is not something you'd ever think about as a kid. You just want to hear how long it takes for you to hear the sound. Any questions with the steps up there? So that question took 10 minutes to go through. Probably takes you 3 if you actually do it on your own and I wasn't talking. All right, takes your time, do it well, do it right. Any questions with the process? So up here, I'll add solve. I should put, if you're writing this down, with equations and units, and then 6 is our therefore statement. Notice how there's no like negative 9.8 up there, right? Because it's not a vector. We don't care, right? We don't care that the initial velocity was up, but the displacement's down, like we did in kinematics, right? So we don't care about that stuff because it is scalar. which makes solving projectile motion questions a little bit easier when you do it this way. All right, next question then. This might be as far as we get today. Then we get the spicier one. Oh, Rick changed the pronoun up there.
Because it's still not moving. Like right before it comes to stop.
Second.
Oops. Because like in this one, like right. Actually, no. I think you're right. Actually, because I don't think it's moving. Never mind.
All right, stage one, system diagram. What's different with this system diagram than the one we just drew? Any ideas? Oh, think about that. Oh, here. Yeah. Yep. Okay. No problem. Bye. Two. There's some mail in the library. You can go down after class and stuff.
Okay.
Go to lunch. What's our trick when we have something involving a spring? Do you remember? Mariana?
Don't you have to draw a before and after picture?
Yeah, you gotta draw before and after when you have a spring, right? Because you have to show the stretch or compress. Or you can't just do one diagram for this. So I'm gonna keep it simple. Here's my wall. All right, here's the bumper before it hits the wall. All right, just as it hits the wall here. And then I got to do the rest of the car. A terrible drawing. So our X value is how much the spring has been compressed. Right? We do have an initial velocity of the car going into the wall, right? And then you have the compression of the spring. However you draw that, you do you, right? Figure out what you want, but you have to show that the spring is compressing here. That's the whole point of the problem. What is the energy transformation equation for this one? What do we have going into what? What do we start with? What do we end with? Jackson, what do we start with here?
Kinetic energy.
Yep, good. 2, what do we end with here? Yep, all right. Okay, so we start with kinetic. If we're going into the wall, and then we end with elastic because it's coming to rest. Do we care that there's sound and all that stuff going on? No. Because in our world, sound does not exist. In the physics world. Okay, so we can go through our steps here, right? So doing the same kind of weird table values that we did before. We have the mass of the car. We have the speed of the car. We have the K value of the bumper. And we have the X value, which we don't know, but we know it's in meters. Okay. So we're checking off our list, right? System diagram, energy transformation, table value. Our law is next. So we have our EI is equal to EF. What's the next line say here? Skipping the long version. What goes next? Ashley, what goes on the next line? Part E.
Isn't it EE?
Yeah. Yeah, good. Alright, so EKI equals EEF. Alright, so we put in our equations. This is 1/2 MBI squared is equal to 1/2 K X squared K and XF. It's the final compression. How can we simplify that line? Not that we really have to, but we could. What's the common factor this time, Maddie?
The half.
The half? Yeah, half's the common factor. So let's get rid of that. And what's XF equal to when we rearrange it? Eric, what's XF when we rearrange it here?
XF is equal to MV squared divided by K square root of
Perfect. First has to be 0.09. I don't know what the real answer is. What's the real answer?
That is the real answer.
Like right on? Oh, okay. A while since I've done it. Okay, there you go. And then you can talk about the Air Force statement. Therefore, Jaden's bumper compresses 9 centimeters when she hits the wall. Right, same steps though, right? Same steps as before. Let's take a look at this one. Alex not here today. So the questions that we just finished would be in the medium medium range. Mild would just be what we started off with today, which is the plain old equation. Medium's putting things together. This one's hot, bordering on extra spicy. So take some time, draw a good system diagram. That's the key to this question. This is another question we're going to get done before the end of class today, but we can do a good system diagram. Okay, so our initial stage, right? It's a spring question, so we have to draw two different diagrams to show our stretch of our spring, right? So diagram one, we have Alex sitting on top or standing on top of the bridge. Nothing exciting happening there. Picture number two has Alex at the bottom of the question. We don't care about the in-between when he's actually moving. So if I draw the in-between, bridge again. Somewhere down here at the bottom. Okay? We have the top and we have the bottom. There's a lot of thinking going in here. That's why this is a spicy question. A hot question, right? So we have the top and the bottom, and again, we don't care about in between. What can we label the problem? So when we go through this, right, we know we're changing in height, so we have to draw a reference point. So I'm going to draw his feet, because that's the lowest point of the problem here. Let's go all the way across here. So I'm going to say that his feet level is going to be where we measure our height from. Because I don't know how tall he is, so I don't know how much his head has changed spot. Okay? We also have to measure our stretch value, right? So for our stretch value, I guess I could do our initial height, the whole distance to the top of the bridge, where his feet were at the start. We know our stretch value has nothing to do with this picture over here because we can't really see it. But we know that our stretch value is going to be our, what does it say? 25 meters. We have a 25 meters where it doesn't start to stretch yet, right? It's unstretched length, and then it's going to stretch whatever that final distance is. Right, so that's that second sentence there. In its relaxed state, it's only 25 meters long. And we know the whole height is 45 meters, so that whole height here, 45 meters. What type of energy do we have at the start? What does Alec have at the start here? We have three types of energies. Brennan?
Gravitational potential energy.
Good. He has gravitational potential energy at the start. He doesn't have kinetic, he's not moving, and the bungee cord hasn't stretched yet, so he doesn't have that either. At the bottom of the problem, what type of energy does he have? And?
Gravitational potential energy and elastic potential energy.
Only one of those two. Depends on where your reference level is, so you're not wrong. Depends on where your reference level is.
So there would only be elastic
Yeah,
potential
there's only elastic in my question. If you made the water your final spot, then you would also be right. Based on my question, there's no gravity at the bottom. Right? Alright, so the bell's gonna go. So I'll try and answer this question tonight. See how it goes. If you have the K, if you have the mass.
Which homework was tonight? This one?
You try some of the homework. I'll pull them up on the screen here. Yeah, so the questions in 4.4 doesn't have elastics in it. And 105.4 has, or 4.5 has elastic potential energy in it.
So 4.5.
So between the 2 days, we're gonna do them all. So choose one. Do what you want. As I said, some of them are easy, some are hard.